Build Show Live 2024 conference classes are brought to you by Builders First Source, Huber Engineered Woods, Pella, and Sasco. This session is sponsored by Polyguard.
Jake Bruton here for Build Show Live 2024. The Build Show is over. This is a wrap. I want to say thank you to one of our presenting sponsors. It is Huber Engineered Woods. They are the makers of Advantech, X Factor, Zip System, Zip R, all of the accompanying products with that, all the things you know and love, and I think they are a great representation of everything that Build Show Live represents. We're trying to move the industry forward. We're trying to innovate. We are trying to be better at every turn, and I think that's a good representation of what Huber and Build Show are together, and I think it's great that they're a sponsor. They're also a good partner for us at Aero Building. We've been working with them for 20 plus years on the Advantech front, more than a decade on the Zip front. They help us build our energy efficient homes. Their tech support and their sales team are always there when we call, and I can't think of a better partner in this industry when we start talking about systems that allow us to do our job in a better format. So Huber, thank you for your sponsorship. I can't wait till next year.
Okay, we're going to go ahead and get started. This is why I'm a wingnut. Maybe you should be one too. I have a co-presenter. This is Cody Pelletier from Laurel Windows. He represents Ocnoplast. He's going to help me with part two. There are two parts of this presentation. The first one's on the wingnut testing of a bunch of different stuff, including pressure-sensitive adhesive tapes. But that's not terribly new if you've been following a bunch of stuff that I've written over the years. The second part is going to be about an innovative way to install windows. And so let's deal with the 800-pound gorilla in the room. So these hats are really important. And so just a couple of notes. If you happen to be traveling with this hat, hide the hat. My wife was watching me pack, and she said, so where are you going to put that? I said, well, you know, it's kind of awkward. I think I'll just hang it off the back of my backpack. And she goes, that is not a good idea. So that's the first rule. Rule number two is don't try to explain the hat. Rule number three is when you've learned not to explain the hat, the third thing is don't say it's a long story. I had a flight attendant and a TSA agent. When I tried that, they said, oh, I got time for this story. And, you know, and then the fourth thing and last is never put the hat on in public. Okay, so I'm going to put the hat on. Yes, we're amongst friends. So the last thing about the hat is that I really don't like people to interrupt my presentation with questions. So if you have a question, you have to stand up and you have to put the hat on. And then everybody's going to pull out their cell phone to get a picture of you with the hat on. Okay, so hold your questions to the end, please. So the last thing about the hat is that it is OSHA-approved protective gear. Okay? Anybody got any ideas why this gear could be protective? From lawyers. The whole reason when my friends and I that were building colleagues from Brattleboro, Vermont, the whole reason we came up with Wingnut is, well, we're going to be testing building materials, and building materials are made by manufacturers. What if they don't like what we're doing? Oh, I know, we'll call ourselves Wingnuts. Who in the world would sue a wingnut? And so far, that's worked. Never had any litigation against us for the testing we do. But it's very important to understand that the testing is anecdotal. You know, this is done without funding, and so we're trying to get a sense of what's happening with building materials. I'm going to explain to you why we need to do this in a moment. But the key is that anecdotal is not statistically significant. So we're just collecting information. And I'm going to come back to how we might change it from anecdotal to something more significant. So a big part of the work that I do is benchtop or in a laboratory testing. Now, it doesn't look like a lab, but I mean experimental indoors. And here what I'm doing is I've set up an easel. I've put tar paper on it. I've got infrared lamps here that do about 500 BTUs per square foot, which is direct sunlight. And what I'm measuring is, with the theatrical fogger, what happens to the fog. There's never been any research about what controls movement of air from soffit to ridge, right? So I'm just a wingnut trying to figure out what are the things that control how much air, how fast it moves up an assembly. And then after that, I go outdoors and I try it on actual buildings. And I've learned a lot, and there's blogs that you can read about this. We're going to focus on PSA tape testing here. But that's the method. Develop an experiment that can be done in a basement or a shop, and then take it outdoors and see how it really works. So here are all the different blogs that I've written, mostly on Green Building Advisor, but also on Building Green, where I used to work. A lot of YouTube videos as well. And we're not going to talk about any of these except the PSA tape testing. And the more kind of groundbreaking part of this presentation is about windows anyway. You can go and find these and learn about the testing that I did with each of them. They're very different, but the idea was to, well, let's talk about why we need this testing. So the first thing is lab test conditions. The substrate all pressure-sensitive adhesive tapes are tested on is stainless steel. Nobody in our residential side of the business ever attaches anything to stainless steel, as far as I know. It's a perfectly clean substrate. In fact, it has to be acetone washed. It has to be 70 degrees Fahrenheit for 48 hours before you test. So everything is stabilized. It's dry at 50% relative humidity. These are laboratory conditions. You never trust somebody who has clean, trimmed fingernails as part of testing building materials. Surgical scissors and not a utility knife. I mean, come on, this is what really happens. Bare, soft hands. Can't trust these people. So what are the job site conditions? It's usually cold, dirty. This is my favorite. It's wet. So imagine the conversation going on between these two fellows. I thought you were going to wear the black trash bag for your raincoat today. Or, do you think either of us can get hurt if we use the circular saw this way? The other thing about wingnut testing is they're not really rules. They're kind of like Pirates of the Caribbean. They're guidelines, right? There's usually alcohol involved with wingnut testing. So what we're looking for is it relevant to the field? Can we repeat it? How difficult is it to do the testing? Because doing lab testing is inherently very difficult. And then it's a sniff test, right? When you run an energy model, the way to figure out whether it's relevant or not is to perturb the variables and then see if the changes you make sense. And so the sniff test is, are we getting what we want from this test? And it's got to be transparent, so we're doing this for free, the Wingnuts in Brattleboro and we'll come back to who these people are in a minute. But we don't hold anything back, And then it has to be cheap. It can't be expensive. So if you're here and you don't recognize this slide as content you've seen before, you must be a narcoleptic, I guess. This is what we're talking about: energy efficiency, durability, and continuous control layers, and here they are. So this drawing is one of Steve's, but back when we started Green Building Advisor was developed by Fine Home Building and the company that I worked on, Dan Morrison from Fine Home Building and me from Building Green. We developed this website together over a 2-year period from about 2007 to 2009. We released it at IBS in 2009, which was a really perfect timing to releasing a new tool for building in IBS 2009. But so Steve did 1,000 drawings for Green Building Advisor. And NEHB said, oh, Peter, we know you from the Research Center. We hear you're working on this new information resource with fine home building. I don't know how they found that out. It was supposed to be a secret. But we'd like to use that in our new building science training 2-day thing. And I said, wait a minute. You do understand you can't have any control over the content. Oh, that's okay. And I thought, oh, come on. National Association of Home Builders is going to let, you know, a Wingnut make up the curriculum. But we did that. And at the first International Builders Show, I've got these slides up, and I'm humming along about halfway through the second day. And a guy raises his hand in the back, and he says, hey, you've been showing a lot of these details. It's weird. Every single slide has tape, all joints, vertical and horizontal, and continuous bead of sealant. But all these beads of sealant and tapes, they're buried inside the assembly. So you've been flapping your jaws about buildings have to be lasting a long time. You said 100 years. And at that point, you get that feeling in your gut like you know that your pants are about to fall down. Because what he said was, how do we know how long these things last? And I thought, I have no freaking idea how long beads of sealant last or tapes, right? So I went back to Building Green and I said, I got to learn all the stuff about ASTM testing and off and running because I didn't understand how the materials worked. So we're going to start with PSA tapes, pressure sensitive adhesive tapes, and they're pretty simple in some ways. There's a backer, and then there's the adhesive, and there might be, well, so the substrate, that's part of the system too. What are you sticking it to? But there can be a release paper, because if you make a tape that doesn't have a bond break on the other side, you would make the roll of tape and then throw it out, right? Because you have to be able to detach it. So if you want to change the properties of the backer so that it's not just a bond break, you've got to put in a release paper, right? So that once you put in a release paper, it frees you up to change the properties of the backer, which could be really important. This is a partial list of all the tests that you can do with pressure-sensitive adhesive tapes with ASTM. Now, why do we need all these tapes? Well, part of it is so that manufacturers of the tapes can pick the tests that prefer their products, right, as they look through the list. But it's completely overwhelming. Okay, so how do we change this into Wingnut testing? So this is Dave Gothier standing up here. He owns or runs, as the president, a structurally insulated panel factory. And you know the problem with structurally insulated panels, you put a foam joint between the two panels, and the panels move over time a little bit, and about 20 years down the road, you get a hairline crack in that foam seal, and now you've got warm, moist air making its way up and you end up with condensation. He said, I need to have a belt and suspenders approach. So what he wanted was the best tape he could find to span the joints on the top side so that maybe when the foam sealant cracked, the backup would be the tape on the top. So he was really interested in how long these tapes performed. But you can see here we're using a tensiometer. The tensiometer moves like 1/8 of an inch in 30 seconds. You know, this guy's like, that guy took the last beer. You know, it wasn't telling us much. And one of the things is, how do we get the stress that we're trying to measure to mimic what's going on? So we tried the tensiometer. We didn't really learn much from that. So we moved on to this test, which is one of the most popular tape tests. It's not actually 3564. It's 3654, if you look it up. But method A is where the methods are different directions of pull. So this is an inline pull. You can do a 180 pull. So you would have like this, and you strip the tape off this way, or you can do a right angle pull, right? So the tape's on this surface and you pull it down. Those are different methods. So you can see here, this is pretty cool. They just let the test go. There's a timer on each of these cells, and when the metal weight drops, it completes the circuit, and you know how long the tape lasted before it dropped off. So we were trying to get a sponsor, and we couldn't figure out how to make beer cans work for this. But our tape testing, to start, was about 5 or 6 different tapes on 5 or 6 different substrates, and we put a kilogram of sand in each of these, right? And we put it in a place that was exposed to the humidity content of the air and temperature. So these tapes did not see any ultraviolet light, and they didn't see any direct water, okay? That's an important part of the test. And then we recorded the temperature and relative humidity on a rather casual basis. So this was at Dave's plant, and well, this was a data logger, but we would go out like 2 or 3 times a day and record as close as we could when a tape dropped, okay? And we learned a lot about how the tapes were adhering to different materials. But then we got talking to each other, it's like, how did we pick 2.2 pounds, you know, or how much force is that? We didn't really understand the forces. So Dave said, I know what we ought to do. The tape on a window, it bellows, right? It gets pushed in, gets pushed out, gets pushed in. Hey, let's try that. So this is Dave had one of his welders make up what we call a pressure pig, right? So there's a pressure chamber here with a hole in it. The substrate goes over top of that with the tape, and then you just apply force, right? So that's a job site pressure, right? Like, well, okay, let's turn it down as low as we can, maybe 2 psi, and let's see if the tape fails. We blew that tape right off of there. So I turned to Dave and I said, how much is 2 psi? That doesn't seem like much. That's 7,000 pascals, right? So what we learned is that those tapes are going to fail in Category 5 hurricanes and tornadoes. So Dave replaced with an air mattress fan, and he accidentally put the fan perpendicular to the inlet. So what does that mean? If you open that up a little bit, do you get negative or positive pressure on the gauge? You get negative, because it's a right angle, you get that Venturi sucking force, and then as you shut it down, it switches to positive. So it's like, hey, all we got to do is be here and throw that lever back and forth. Like how many times? Like, that's not going to work. So here was our round 4 testing, because we said, what do we want the tape to hold to at a window? Well, it actually has to hold to 2 substrates. It's got to hold to the sheathing, and it's got to hold to the flange. And all the flanges are made out of vinyl and aluminum. So in this one here, we have half the tape. So what we did is we took approximately 1 square foot of tape. That metal rod is a spanner to distribute the force over the whole tape. And then half the tape is stuck to, in this case, a metal flange, and then the other side is rough OSB. So that's how it would operate if you put the tape up before you put the house wrap up, okay? And we figured out the math. So here's the math. I'm not going to spend any time on this. What we did is we wrote a 4-page protocol, and we sent it to 4 major tape manufacturers, and we asked them to review the protocol, and I put a picture of a Wingnut hat at the top of the document. And we expected to get dope slapped and told we should find other things to do when we drink beer. But what they said, all 4 manufacturers, was, that's pretty good. All right, you got the right force. So this is our assembly. And so from the underside, you can see that the tape is being pulled. We don't have any, we can't push it. We can only pull it with this method. But what we did is we took the weight off and put it back on. Took the weight off, put it back on. And this is what it looks like from the top. So we had dado cuts because that represents the rough opening space that's being spanned. And then what we did is we squirted with water the back side to represent condensation and the front side to represent water that got passed. And then we put it in a shed, and I would go out and squirt, take the lids off, put them back on. We did this over about a 6-month period. And you can see we were wetting them from that. And the OSB is getting wet, okay, which also is going to be important. And then we recorded when they dropped. And a lot of data there. But they only dropped when there was a sharp temperature difference or a big change in relative humidity, or both. And the reason for that is you've got the tape, the aluminum, and the OSB, and when you wet them or change the temperature, they are all responding differently, all right? You know, the OSB takes longer, but you're introducing stresses to that system. And so what we're trying to do is figure out what we have to do to load the tape the way it would be loaded in reality. So that's, you know, why we came up with this process. The flanges dropped more than the sheathing. Well, that kind of makes sense, right? Because the flanges are not porous. You know, they have no ability to absorb moisture. And the contact area is just what you get. You don't get nooks and crannies that you can get. When you pressurize a piece of tape, it goes down into the little nooks and crannies and bonds there. You can double or triple the surface area content by having a variegated surface. The two flanges, they have no variation. You know, they're smooth and no additional. So you can see here that this tape has let go. It's let go off the vinyl in this case. You can see there's a lot of creep, right? So if you put the weight on and take it off and put it off and take it on, particularly the acrylic tapes, they've got a lot of capacity to absorb before they let go. And then you can see down here, same thing. So that's PSA tapes, except for the demo we're going to do. And Greg, I'm going to need you to help me out here. I have a section of the Building Green website called Sticky Business. So if you just go to Building Green and you type into the search engine Sticky Business, all the blogs that I've written about pressure-sensitive adhesive tape testing and liquid sealants to some degree, they're in front of the paywall. You don't have to pay for them. So if you want to cover more of this material, you can. Okay, so here's what we're going to do. I have set this up, Greg, if you can come in here. And so what I've got here, starting on this side, I've just got a piece of zip sheathing, so the surfaces are all the same, and I've got 3 different high-performance acrylic adhesives. I'm not going to tell you which ones they are. And what we're going to do is we're just going to do a fail test, and it's a perpendicular pull. I don't have a dado in the back of this because I'm not looking to add moisture or not. So what I'd like to do is have what's your name, sir? Okay. Oh, great. All right, so I'm going to put my safety gear on. You're going to put your safety gear on, and you're going to do the first pull. Okay, so Greg is our photographer. He's going to come over here and help us out. All right, and I'm going to I should turn this on, right? Yeah, probably. And I don't want to do it in kilograms. I got it in pounds. Okay, so what I want you to do is use the carabiner, and I'm going to read, and I'm going to read as you pull. Just go straight down. All right, so we got 42 pounds, 50 pounds, and we failed right at about 42, or around 50, okay? So remember, we've got about a square foot. This let go at about 50 pounds per square foot. That's a lot of force. We're simply doing this to show just how much it takes to get it to fail, okay? So thank you very much. That's my hat. Take your hat off. Put this hat on. Everybody got their camera ready for this guy? Okay, there's another high-performance tape that we're going to do. So we're going to put this in the carabiner like this, and we're going to get the... Oh, yeah, you're from Aussie, right? Yeah, you've got an Australian here. You're probably jet-lagged anyway, so it doesn't matter. You couldn't do it in either of the units. Okay, so this is tape number 2. These are all high acrylic performance. 18, 25, 34, 50, 51, okay? And interestingly, different type of failure. Well, maybe not really. In a sense, we got to a force high enough that this spanner bar failed in its action. That's not a tape failure. That's not a substrate failure. That's just the test failure, right? Okay? Thank you very much. Give me a hat back. Thank you. You ready? Another Aussie. Yep, so we got, this is the 3rd tape. All right, so we're going to put it in here. And we're going to turn it on. We're at pounds. Okay, this is the third high-performance acrylic adhesive. Hold on, I got to be able to see this thing. All right, go ahead. Yeah? Nice and steady. Whoa! 80. You probably broke my scale there, buddy. These are expensive, you know, the scales. Okay, so the moral of this is, I don't care which acrylic tape you buy. If it's a high-performance acrylic tape, the holding power is so much beyond what we need. Well, let's try this one. Aaron? This is a pretty subdued crowd when I'm doing wingnut testing. This is kind of weird. Hey, by the way, it's politically correct. There's a left wing and a right wing.
Does it matter if it's on the right way?
You look about the same either way with that hat on, Aaron. All right, so what I want you to do, I want you to take this one. Oh, by the way, we end at 10:30, but there's nothing after this, so we can hang around and do whatever we want for as long as we want, but don't leave early. Okay, Aaron, so what I want you to do, I guess I don't need to hitch that one, right? I'm going to turn this on. I think we did break it. Oh, the batteries fell out. Hey, you got your readers on? You got to put these in the right way.
All right.
I got to find another battery.
I'm missing a battery.
There we go. I got extra batteries, believe it or not, because I was afraid I'd lose them or they go dead. All right, there's a panel on the back of that. All right, let's try without the panel. Okay, so
This is extremely scientific.
there we go. Kilograms to pounds. All right, go ahead and give that. Tug gently, please. Real gently. Real gently. Okay, that failed at about 40 pounds.
All right. So good news, I lost both your batteries, but I found the backing.
Okay, so while you're up here,
Put it back together?
yep.
Okay.
And I'll take this off. Who's next?
Oh, you got to give me the battery if you're going to take the hat away.
Oh, you need those two things. Sorry. This is very stressful for me. Jeff King's going to come up here and help us out.
He's very passionate about his scientific equipment.
You hear what he said? Put some tape on the battery cover. I love it. Okay, so this one, we got to take this off. All right, let's, yep. Go slow, because I'm slow. Okay, go ahead. I'm going to pull down. Okay. That was about 70 pounds. Okay. This one that dropped by 40 down to 40, so about 25%, I didn't roll it. And this one, if you come up and take a look, Greg, I might have to turn my headlamp on for this. This looks just as goofy as the hat, but that's good. Clearly I need to put the hat back on. Jeez. You're not allowed to laugh. You're just the videographer. Come on. I rubbed silty soil in here, okay? When I did this at home with clay, the holding power dropped by 50%. Why? Because the soil is a bond break. So if the soil gets into nooks and crannies, you're only hitting the high points. So the moral here is, I don't give a crap which high-performance tape you choose. The tapes are pressure-sensitive adhesive. You got to have the tape rolled thoroughly, and the substrate's got to be clean. All right? Now, I'm going to show you this one here. I tested this one at home. Soil wasn't close by. I was working in the garage, but there was flower pots. So I took compost, and I put it and rubbed it on the zip wall, waited 24 hours, wiped it off. I can't get this one to fail. It exceeds the capacity of the scale. What the hell? So is this still on? Yeah. The moral here is when you perturb the system, you're going to get results that don't make any sense, and that just leads to more testing, okay? So that's pretty much it for the first round on the tapes. And now we're going to switch gears, and I'm going to have to go back to the PowerPoint. How am I doing on time? Am I way over? No, I'm pretty good. I've only been going a half an hour, right? That's like right on the money, halfway through for part 2. Woo! Okay, so Cody and Aaron are going to help me out here. And Aaron's with Pella. He's going to help us out in just a second, too. And I need my clicker. All right. While my window gently weeps. This is a project that we're going to learn a little bit more about. I'm going to show you 3 projects. Oh, that's Jake.
He's proud of himself.
Yeah. Anybody see what's going on in this slide? Here's the window weeps. This is installation at International Builders Show. So they had a different company install the window. And so they installed it, spun 90 degrees. So this first project is at the top of a mountain in Vermont. And the guy who bought this property and built this house is a Bitcoin inventor guy. You know how he picked this location? He was hiking in the woods with his cell phone. And when he got the strongest signal, he figured out who the owner was of that property, and that's where he built his house. He located it for cell phone reception because it's in the middle of nowhere up here. So he's got this tiny sort of very high-performance building. I know the builder. He's one of the members of the high-performance guild that we had in Brattleboro. This is high-performance triple-pane tilt-turn windows, a lot of fixed ones. A lot of glass in this building, good reason, because it's just a gorgeous view. And I got called in because these windows leaked. Now, this is a high-performance building with a high-performance builder with a high-performance window. I know his crew, and yet they could not install those windows properly. So it led to a huge problem for both the builder and the homeowner, but they failed to install the windows the way that it was drawn. And you can see part of it is that they closed off the weeps in the windows. This is another project in the Northeast. High-performance builder, fantastic reputation. High-performance architect built this home for her family, or designed this home for her family. That's the view. So again, these are very exposed sites in a cold climate. That's what it looks like from the outside. This is what it looked like on the inside. High-performance builder, high-performance architect. These leaked before they even spray tested them. This is a project that was built in 1990. It won an architectural award in 1990. This is what happens when an architect has an LSD trip. Everything here is curvilinear meeting linear. You know, this huge fin that comes out. This is the stair tower. This is called the lemon slice. This lemon slice changes in arc, changes in, the bottom drops out, and every single one of these windows is square, okay? And the toughest part was, so that's the stairwell again. This is from the outside. This window is 20 feet tall. Had to drop it in with a crane. The crane had to come up over top of the building. This is on Stratton Mountain. It's at the top of a ridge. It experiences 100-mile-per-hour winds routinely. This is the rotunda. It's a 40-foot tall circular column that comes up right through the middle of the house. That lemon slice window, it dives right into the back of this. So the structural connections are absolutely insane. But all of these windows, they're square. So to install them, the openings are flaring out, right, because it's a circle, And not only, they don't have any reference for where to install them, but they had to get the trim right per the customer. So what determined the location of the window and the opening was not anything other than the trim has to look the same as you go around the rotunda. All of these windows leaked. This is about a $2.5 million project. It's going on its third, almost its fourth year. The retrofit is $4.5 million. Everything in this building was rotten. I have some photos, but I had to take them out because I didn't have enough time. But all these windows were installed wrong. Now, that was 1990. But this is what it looks like from the inside with the new windows installed. By the way, I took a blower door and set it up at the bottom of the rotunda. I think I put in a duct blaster in. These leak like a sieve, right? But this is the drawing. So this is so complicated. We went iteration after iteration because these big windows have big subsills. And we couldn't agree on where do we put the flashing for the assembly. Do we flash it at the top of the window unit? I'm sorry, at the bottom of the window unit or at the bottom of the subsill? Because they kind of wanted to make it half of one and half of the other. And I said, that's not the way water works. So did they get these installed correctly? Well, what are the dotted lines? That's a weep. Where's the weep? Right? So we have a major problem in our industry with how complicated and how unique window installations are. So this is one of Steve Basic's drawings. He knows I use this slide. This is a custom installation in a building, but it's difficult, right? Because you could have a builder and carpenters that understand this stuff, but it's changing all the time. And it changes with all these different parameters. And so if you think it's bad that we have high-performance builders and architects and trades folks that can't do this right, what's happened to the rest of the windows? So what's the problem? The installs are too complicated. They're often customer unique. There are too many variables. And as we build deeper walls, or we put rigid insulation on the outside, if you have to drag the head flashing out over top of your insulation and your WRB is not in the same plane as your flashing, that gets really complicated, right? So there's all these moving parts, and if a carpenter shows up at a job site, it may be something he or she has never seen before. Now the details are there in a drawing, but you got to translate that to the job site. The manufacturer's instructions are limited to the simplest installations. So if we complicate the installation, we're going to have to deviate from the manufacturer's installation instructions. And then the biggest problem is, if a window fails, it's just, it's just everybody pointing their fingers at, well, the architect's drawing wasn't quite right, or, oh, we switched materials and we didn't know that that would have this impact. We don't have clear responsibility. And this is one of my major problems with our industry, which is, we're introducing more and more products faster and faster, trying to improve the performance of the materials. But that's not what happens. It's the assembly. And we're making them exceedingly complicated, and we are setting ourselves up for failure. Okay. So now I would like Aaron to come up, and we're going to have Greg come up again. I think that, how many people have seen the Pella Steady Set system in, okay, if you haven't seen it, you've been walking in the wrong door at the show thing here. But Aaron's going to show you real quickly how this system works.
So it's an interior install rather than going from the outside. So it allows you not to have to carry this up the ladder with all your materials. So on the inside, before you install, you'll take the bracket, flip it around, snap it in. So it's based on what wall depth you're designing it for. And then you'll install the unit. It's got 1/4-inch shims already built in. So then it allows you to leverage the unit or put your sealant in. And then it's got the
In my timeline, I was working on an interior install about 6 months before I learned about what Pella was doing. But this is going to change the way flange windows work in buildings, because the window manufacturer is really seriously dipping into the area of installation. And Aaron's going to have a setup back there when we're done. Thank you, Aaron. Appreciate that. And I know some of the engineers that are in R&D. Actually, one of them worked with me on tape testing about 10 or 12 years ago. So the R&D people at all your product manufacturers, you know, really good manufacturers of any product, they've got really strong technical teams. So if you're having trouble getting technical information on a product, go look for a different product. Because without those people who go out in the field and develop the products, you're not getting what you're paying for. All right, so there's the Pella steady set system. What about another approach? So I often make this joke. So I don't know what the least expensive car is in America, but let's just say that's a Chevy Spark. Okay? Pretty close. I can take a 5-year-old Chevy Spark, drive it 70 miles per hour into a rainstorm, and it will not leak water. We build houses that sit still that leak water. Right? Why is that? You build something in a factory. Industrial engineers, does anybody know what first time I heard that, I thought, what do? You engineer industry? Industrial engineers are all about quality control and inside factory settings. So it's industrial engineering. But if you're making a product that requires really high performance and you're doing it in a controlled setting, that, you know, you can make a lot of things happen. So I got to thinking, why don't car doors leak? And the answer is they use gaskets, right? And they're two-part gaskets. There's a gasket that's continuous. So my wife comes outside, and I'm taking all these photographs of the gaskets, and I've got a turkey baster, and I'm squirting water in there. And she says, I'm pretty sure you don't have a girlfriend. And, you know, you do this at home, so, like, knock yourself out, buddy. I'm going to hurt the car. So I started to look at all the car gaskets. And so this is an old drawing. But what's interesting about this is I must have photographed and sort of water tested about 25 different vehicles. If you go back 20 years, the gaskets about 20 years ago are almost identical to the ones we're using today. But if you go back before that, they're all different. So the automobile industry is working with some sort of group that is learning, and they've pretty much arrived at the optimal system. Okay? So one of the secrets is it's a drained rough opening, right? So the water gets in at the top, but the gasket's carried around. It comes at the bottom of the door. And, of course, the doors are flush. There's no protection by design. The water is going to get right in there. The question is, what happens to the water after it gets in? These gaskets are continuous. They're not, I couldn't find a weld anywhere. So these are going to be wicked expensive gaskets because they're custom for the shape of the door. You peel back the gasket on either the frame or the door, and there's holes. They're not weeps. They're just perforations hidden inside the folds of the gasket. We'll come back to that in a second. The car door gaskets are heavily shielded. So they're the only place that there isn't a really big distance between the opening between the frame and the door and where the gasket is. The only place that's not hidden is right on the top of the window. And that's the only place that the bulb gasket is supported by a thin gasket, right? So they're protecting the head in a different way they do the rest. So I went to a car wash. I used my business card, you know, because it's a business expense. I put on my hat. And I'm blasting the living daylights with that really high pressure, and I'm adding soap. I mean, so I took, this happens to be a straw wrapper, but I took a bunch of porous paper, and I placed it so that it was caught in the car door, but it stuck out into the space where the gaskets met, or beyond that, right, into the cavity. Blasted the whole car, had these located on different locations in the door, in different doors. Not one of those pieces of paper ever got wet. So it's shielding, right? It's this big space. The water tries to go in, it hits a big space, its force gets dissipated. So I'm thinking, wow, I got to talk to a gasket engineer. So it turns out I had done some proprietary work for a car manufacturer that was trying to develop modular housing. And I thought, hey, if anybody makes the transition from, because we've got these cars that are made in a plant, we've got these houses built on job sites, we need to like have them talk to each other. And that's exactly what this manufacturer is trying to do. So this is like 6 years after I had worked for them, and I called my contact there and I said, hey, you work for the car company, right? He goes, yeah. And I said, I need to talk to an engineer who designs the gaskets. He's like, why? And I said, well, I want to figure out if I can use gaskets on windows. And he said, we don't really have any interest in your process. But he said, I'll bet you that one of those engineers is going to be tickled pink that somebody wants to understand what they do, right? So lo and behold, I get a call a week later, and this guy says, I talked to the head of the Automotive Engineering Enclosure system for cars. So the enclosure system is the windshield, the windows, the doors, the trunk, the hatchback, and the roof windows. That's all that they do. One of the most important part of an automobile is all those openings. So I was told I could talk to him for 1 hour. We set up the Zoom, and here's what I learned. First thing he said about gaskets is, it is rocket science. It's incredibly complicated. And the reason it took them so long to move from variation to agreement is that, you know, a lot of gaskets didn't work the way they wanted or didn't work over time. Seals serve multiple functions, but in the car industry, it's shakes, rattles, and rolls, right? That's their biggest enemies. So the gasket system is the primary, or the first objective is sound reduction, acoustics, not water tightness, right? So their gasket system is, the primary thing they shoot for is no noise. The bulb gaskets, it's really critical that you protect them from ultraviolet, right? Which is one of the reasons they're not, except for that fin gasket across the top of the door edge, all of them are buried because they can't see chemical exposure. So a problem would be acid rain or something like that. But the biggest problem is ultraviolet. It's the turning the corners that's going to be the problem. The reason the car doors have these sweeping, because the other thing that's going to happen with the gasket is stiffness. Because the relationship between making something that can be so supple to do other shapes is also fighting the stiffness of the gasket, right? They're trying to find that sweet spot between the two. And part of the reason you want to combine or have tension between stiffness and flexibility is corners. They're always the problem. And there are about 4 major manufacturers across the world of car door gaskets. And they all have secret formulations. And even the auto companies don't know those. Those are proprietary. Although what he said was they perform pretty similarly, right? I don't know if they switch from one manufacturer to the other I don't know the answer to that question. But the last thing is that before that vehicle rolls off the assembly line and is approved for sale, the last thing they do is a bulk water test. And he wouldn't give me the details of that, but he said, it's a lot of water. So what's important, though, is the difference between automotive gaskets and what we want to do. For the automobiles, there's a lot of movement, right? The car goes over a bump, and everything flexes. So the reason they need two gaskets configured the way that they are is that you have to accommodate movement, you have to maintain a vibration control and water tightness as it moves. And the other thing is the car door opens and closes thousands of times. We don't need to do that. We just got to get it in once. And I asked him about the perforations, and he goes, oh, that's funny. If you don't perforate both gaskets, you can't slam the door. It'll just bounce off, right? Because it compresses the gasket and pops off. Those perforations, and they're hidden so that they don't see water. So, armed with that information, so what do we do? Okay. I think we should rely on gaskets. I think there's an opportunity there, and we should compression click them. You know, just like Pella has the system where you snap it into place, when you get it the right place, we should be able to load that gasket with just the right amount of pressure so that we have it tight enough to make it an air seal. Sorry, a water seal. We're going to install the windows from the interior, and we're going to have a buck. And so, Greg, well, let me go through these slides, and then I'll show you how we ended up with what we have. The gaskets in cars are, let's see, one installed in the window exterior face. Okay, so I'll show you in a second how my first process was to just put a stop all the way around the window and have a gasket to the inside. But then all the water gets trapped at the bottom stop. So I took out the bottom stop. And now what I've got to do is I've got to move the gasket from the face of the inside of the window install to the sill. I'll show you how we did that in a second. We have to flash and drain the buck. We're going to get rid of the flanges. Now, in the olden days, when we had 8 or 10 inch thick walls, we put the window in a protected place. It was always recessed. There are no flush windows on old assemblies. When we switched to wood framing with sheathing, when I was a carpenter first time, you take the wood window unit, you trim it with the casing at the head and the jambs, and then you just slide it in. So now we've moved from recessed to flush, but the entire window is into the wall, right? Flange windows take part of the window and push it out. So it's convenient, but that is really stressing the system. So I think that we have to figure out how to get windows tucked back in. And then we're going to line up the responsibilities based upon the installation system we come up with. And I'll come back to this collective wisdom in a second. Oh, maybe I should do that now. So we did a podcast on Unbuild It probably about 1.5 years ago where we talked about this in vague terms. But it's geometric. You know, you can't talk about it in thin air. That wasn't very successful. Then I went to IBS, so that's February of 2024. I've already got some basic ideas on how to do this. But then Pella came out with their system. I said, well, now I'm rocket fuel inspired to do this because Pella's working on it. So I went to the BS and Beer in Portland, Oregon, and I did a presentation on gaskets. And there were 2 window manufacturers there. And they said, we need to talk to you. And I thought, good, because that's what I want to do is talk to you as well. And so it's important to say here now, this is totally open source, right? I'm never going to make any money off of this because all I want to do is develop a system. I'll come back to that in just a second. So I did the presentation in February at BS and Beer in Portland, trying to work with a couple of window manufacturers. Then we get to BS and Beer in Chicago. BS and Beer in Chicago was the beginning of October, but Kristen Michaels, who was one of the leads on the Build Show, said, Peter, I just saw your PowerPoints from Portland. I want to do that at the Build Show here. And I said, okay, so we'll just take the PSA tape and the windows and put them together. We'll do a presentation. But in the meantime, I'm starting to get traction with a couple of window manufacturers, right? And I said, what I'm really interested in doing is figuring out how we do it with flangeless windows. She said, oh, that's great, because Octoplast is one of the sponsors and we've worked with them before. Let's have you talk to them. I never heard of Octoplast. That was, the BS in Beer was October 8th and 9th, and then started to work with Octoplast in Poland, 6-hour time difference and language barriers. They're really interested in what we're doing, but the head of the company kept saying, you need to go talk to Cody Pelletier in Boston at the Laurel Design window there. I thought, okay, we can go down there, but he's probably going to be a sales guy. I don't want to talk to a sales guy. I want to talk to a technical person. So Steve Basic and I drove down to Boston together, and we're in Steve's driveway, and I've got my little mock-up here, and I said, should we take the mock-up with us? He said, no, it's going to be salespeople, right? So we walk in. We don't walk in. We can't find a place to park. So the guy says, oh, I'll come down and find you. And so this guy starts walking towards us, and he's got a flannel shirt on, blue jeans. His shirt's not tucked in. I think he had hiking boots on or something. We go, who's this guy? Hi, I'm Cody Pelletier. I'm the owner and president. And I turned to Steve and I said, I knew we should have brought the demo. So I didn't have the demo with me, but I had a video clip of it. I sent it to Cody, and he's like, it was like cocaine, Cody. Or a hat. So that was October 18th. We're presenting here November 8th. That is so cool. You got to take a picture for me of this. So Cody's off and running with how to try to do this with the triple pane windows. And so I shipped my demo, which I'm going to show you in just a second, to Kristen Michaels here. And then he's working on his. Tell him about shipping it by air. Well, I was here on Wednesday. He keeps calling me from the airport. Open up the window. I said, it looks fine. It's in a car. It's in a plywood box. It's fine. But he didn't tell me. What he wanted to know was whether the window had blown apart or not in the airplane. Let me do this one quick, and then we'll switch over. Okay, so this was round one, all right? And the idea here is that I have stops, and it doesn't matter what plane you put them in, right? You can move your window in or out, and I've used a stretch tape for the sill here, okay? All right. Greg, can you catch all this? Okay, so everything's flashed. I'm going to spin this around and show you the back side. So what you can see is that is a bulb gasket that goes all the way along the flange until you get to the sill. Okay, I'm going to tip this way, right? Here in this corner that's not sticking, get to that in a point, I switch to the sill. And then these tabs are the right height, so when the window goes in, you won't fully load the gasket. There's about a 3/16 of an inch difference here, and that difference is going to be determined by the properties of the gasket. Remember, this gasket, there's my coffee. I should have spilled it on the window. You can pass these around. That's the gasket from Amazon that I chose. Okay, so how does this work? I'm going to spin this around. No, I'm going to leave it this way. So here, this is a fake window. All right, this is round one. Ignore this for a second, but you just place the window on the stops, slide it in until it's flush, And then, there's your window, okay? And the only thing I have to straighten out is the corners, where I change from one plane to the other, right? That's going to come from a gasket manufacturer. So I showed this to Cody, and now he's off and running with his system. So we're going to switch to this window here. Do we need to, so we'll just tip that maybe, huh? Yeah. Go ahead, Cody. Yeah, we're going to work with the gasket manufacturer on how to weld that shut in the corner. So now we're ready to install? Yeah. Yeah, you should probably take off your hat for this part. So while he's doing that, the switch to neoprene was his idea. And this is open source, right? Home Depot. So here's the process. I came up with this approach, and I'm not going to be able to do it by myself. I don't have an expertise. It's like working with Wingnuts, right? Everybody does a contribution, and you just keep contributing towards the goal of how do we make this simpler. When I tried to do the drawings myself in 2 dimensions, no one understood what the hell I was talking about. I was trying to get Steve, because Steve told me, he said, Peter, you're trying to work in 3 dimensions with a mock-up. I need to be able to draw it to tell what it's going to work. I thought, well, then draw it. But what is he doing? He's doing 19 presentations at Build Show. He's not going to do me a drawing on the side. So we're at the point now where when I show folks this demo and then this demo, we're off and running in terms of improving the system. Todd, who works for Cody at Laurel Windows in Boston, is their architect. He said, Semperit. Semperit is one of the biggest manufacturers of high-performance gaskets that we already use in our triple-flanged windows. Not bulb gaskets, but flanged gaskets. So the next step for us, all right, so we've got the window installed. It's up off the sill. And by the way, one of the really cool things about Pella's system is we should never, ever, ever install windows where there's constant contact between the rough sill pan and the unit. That is like asking for trouble. All we got to do is gap it up a little bit. So Pella's got that nice little skid piece at the bottom. It automatically lifts. Even if you're leveling it, you have free draining space that's underneath that sill. And so what we're going to do now is, remember, it's the shielding in the car doors that takes the force away from the gaskets, right? So the jam extensions are going to, we don't know what this distance is going to be, but essentially that's going to protect the bulb gasket from ultraviolet and from ever seeing any direct force of the water. So we just trim it out with jam extensions. And by the way, the Velcro is, you know, cheap. At 3M, nice. Yeah. You might have to flip it. Yeah, I think you got it. You have to kind of seat these. All right, so you get the idea. And the only difference between these two right now is that this one has not been flashed, right? But when you flash it, the black tape and the black gaskets, you can't see them. So the whole reason we didn't do this one was just so that you could see the gaskets. And then this is important. This is cover metal, right? This is to protect the sill pan flashing from ultraviolet light, and it's going to come up and simply butt up against there. And what we would do, this is just a piece of scrap flashing we found at Build Shop over on the other side of town. This metal flange here would be crimped over to stiffen it at the face here. Remember, all it's doing is protecting from baseballs and ultraviolet light. So what we would do is take the underside of this and rib it with like 1/8 of an inch ribs so that this gasket here was never down on the rough sill. That's pretty shoddy workmanship, isn't it? Damn Velcro. Please, we're not going to use Velcro in the actual, all right, so in about 9 months, I went from not being able to draw this to, we think we have a system that if we can get the right gasket company to work with us, we're going to be water testing this probably in a couple of months. And I think we might be able to do a much better job. So the other goals here were one gasket that's both the air seal and the water seal. Because that frees you up to then, here, with this one, yeah, see, I'm old and he's tall and young. Now, this was my other goal. All the trim goes in with trim screws. If you ever have any problem with the window or the gasket, you pop off the trim and you slide the window out. You replace the window or you do whatever you want, but this is easy removal because these triple pane windows, they're going to last the life of the house, right? So install them in a way like cabinetry so that we can, if we want to, so if you have a house that's 100 years old and the glass technology changes, you better have a simple way of replacing a very expensive unit because you don't have to take this whole window apart and you got spray foam in here. It's just going to be a pain. But if we get the air seal and the water seal up at the gasket, then we can just stuff this with mineral wool, whatever we want. So when we take the window out to replace it, it's just pop the screws and take the unit out. Put it back in. Okay. Got to switch back to the PowerPoint. We run over, but I'm going to fly through this. We're almost done. All right. So the last thing I wanted to say about, I'm just going to put these up here real quick. The problem we have right now is that there's probably a dozen Wingnuts that I know. We need Wingnuts for all across the country because of the climate changes, right? So the testing I do in the Northeast is going to be very different than, so if we had a network of these Wingnuts doing stuff and we had a repository to put it in, we could start to make data out of it, all right? And Nate Gusikoff, who's a building enclosure consultant that sort of, I'm retiring, so I sort of like turning the business over to him. He said, oh, I want to be a Wingnut. But he was starting a company, so he doesn't have any time to be a Wingnut, and so the process is sort of stalled. But at this conference, there is an AI engineer from a major computer company, and he wants to be part of our industry. If we took data from all these points that is anecdotal, but we start to compile it and we can process it, we can not only turn this into data that we all use, but I just learned this yesterday, we can take all that information and tell AI, take all this information and spit it out for homeowners. And then take all the information and spit it out for a builder. And then take all the information and spit it out for a building scientist. AI can tune the information it presents based upon the level of the, so I think what's going to happen is someone's going to figure out how to be the repository for this information. We already have a website. It's called the Wingnut Test Collective that Nate developed in Middlebury, Vermont. But he's not doing anything with it because he doesn't have any time because he started a new business. So I'm retiring. I took all the Wingnut stuff and shipped it up to Nate in northern Vermont, so it's gone. We need a new generation of Wingnuts because the way to have cooperation and share responsibility with manufacturers is we make these really complicated building enclosures and we do it in such a way so that no one is responsible. We're all responsible, right? And so if we start working together as building professionals and manufacturers, be the feedback loop to the technical R&D, I think we're going to be able to tackle problems like this one. Thank you very much.
It's been a great week here at Build Show Live in Austin 2024. I want to thank one of our project underwriters, Polyguard, who is providing this content from our classes, which were amazing in client management, building durability, and building science, where Polyguard has been a leader in air and water management for a long time. We've used a lot of their below-grade water management solutions, but they brought out some great new stuff from their termite prevention to their air control products. Polyguard's been solving things for builders for a really long time, and we're grateful that they're still working to make our lives easier every day. Thank you to Polyguard, and thank you for your continued support of our educational content.